What's up, statistics? This is going to start a new week of lessons and a new unit as well. So this is now Unit 7, probability. We're going to be spending probably like 4 weeks on it. Get it? Probably. So we're going to be spending about 4 weeks on this lesson, on this unit. Probably maybe 3 weeks, but it's going to be a big unit. This is your first unit, one of 2 units. And we're going to start this unit with the 3.1 basics of probability. 3.1 basics of probability. It's actually a very simple lesson. We're going to go through a lot of the basics. Examples, what is probability? Why do we have it? How does it relate to sample space? The stuff that we talked about last week. And then, of course, we're going to go through the summary and the homework. So without further ado, let's get started. So please, again, write your notes, get your notes out, write the essential questions here because I will be checking your notes, not this week. I checked them last week, but I'm not going to check it this week. I'm going to check them next week. I've noticed a lot of you have yet to do homework on Math Excel. I will tell you, you guys, seriously, you will fail this class before you start passing this class, if that is the case. If that's the way you're going to go this route, just not doing homework at all, then I don't even know why you're in this class, to be completely honest with you. I only had one student out of the whole class that basically did their homework consistently every single day. You guys will fail this class before you can even blink your eyes if that's how you're going to run it. Seriously, you need to watch these videos. You need to pay attention. You need to take notes. You need to participate. This is actual real school. If you don't do that, then you guys will seriously see your grade tank before your eyes, like fast. Pay attention. Okay, you have homework quizzes this week. You have a homework quiz tomorrow. You have quizzes this week in general. You have to take notes. You have to pay attention. You have to actually engage, or else it's not going to be a pretty sight. So write down the essential question. What are the basics of probability? How to identify sample space of the probability experiment. This is the objective. You don't need to write the objective at all if you don't want to, but just write down the essential question. I love this meme with Jim Carrey. So probability of not hitting is 99.99999. Yeah, so it's basically 100%. And he's like, so you're saying there is a chance? I love that. Yes, there is a chance, technically. Okay. What are the basics of probability? When you follow along, I'm just going to show this to you guys. When you follow along, you can absolutely use this. So all I did was go to here, the Google Classroom. If I go to the week 2 online, it should already be posted, but the week 2 online suggested schedule, I go down and then I have the note packets here for you. You can go ahead and click that note packet here, and then it's this. Feel free to print this out because you can actually follow along, or you can make a copy by going to File and then make a copy. Okay, so by all means, you can do this, follow along, or if you don't want to do that, you can actually print off my key. So right here, I have the key right underneath. You can print that off and follow along, and it looks like this. This is everything that we're going to be going through today. Okay, so feel free to print off that key and use that to your benefit. Okay, but other than that, if you don't have maybe a printer, if you don't have anything like that, then by all means just watch the video and then write down the necessary notes. I'm going to probably skip a couple examples as we go through here because not all of them are necessary, but a good majority of them are necessary. So what are the definitions? Well, a probability experiment is what we call an action or trial which certain special results happen, meaning counts, measurements, responses are obtained. So what does that mean? So a result of a single trial in a probability experiment is what we call an outcome. Okay, it's an outcome. So actually what happens is an outcome. So if I roll dice, I have dice right here, right? So if I roll dice, what that means is I will get like a 1 or a 5 or maybe snake eyes, 1 and 1. So those are the outcomes we say. Now the set of all possible outcomes of a probability experiment is what we call the sample space. Remember, you can by all means follow along. So this is where we're at right now. You can just print this out, make a copy, and just type in sample space there because that's where I'm at. Okay, sample space. Follow along right here. Sample space, this is the key. Feel free to print out this key even. Don't submit this as your notes. You still have to use some sort of other notes, but you can absolutely print out this key to just help you with your homework. But the set of all possible outcomes of a probability experiment is the sample space. An event is a subset of the sample space. It may consist of one or more outcomes. You don't need to write this down, but a probability experiment, for example, is like you can roll a six-sided die. Okay, the outcome would then be if I rolled a 3, and we would say that is a 3 that we rolled. Okay, a sample space then, so I'm going to move this. A sample space is then for this six-sided die would be 1, 2, 3, 4, 5, 6, because I have those options available to me. Meaning I could roll a 1, 2, 3, 4, 5, 6. I can't roll a 7 with a six-sided die, right? But I can roll 1, 2, 3, 4, 5, 6. That's my sample space. The event, let's just say if I roll an even number, what's the probability of rolling that event? Okay, an even number. Well, that would be 2, 4, 6. So that's 3 out of 6. So my probability of rolling an even number is actually 1/2. Because 3 out of 6 reduces down to 1/2. So you start to see how some of this basic probability stuff is kind of intuitive. All right, let's get into identifying a sample space. A probability experiment consists of tossing a coin and then rolling a six-sided die to determine the number of outcomes and identify the sample space. So how do I do this? Well, first of all, I have to write, I first toss a coin. So when tossing a coin, I can get either a heads or I can get either a tails, right? When I toss a coin, I get heads or tails? Yes? So those are together. Now, I can, after getting a heads, after I toss a heads, I can get multiple other options. I can roll a 2, I can roll a 3, a 4, a 5, or a 6, right? But what if I get a tails first, and then I roll the dice, right? I toss the coin, I get tails now, but then I roll the dice. What then? I can still get a 1, a 2, a 3, a 4, a 5, and then a 6. So how many options is this? I have 6 right here, I have 6 right here. So how many options? Well, I have 12 different outcomes. What are the 12 different outcomes? The 12 different outcomes, and my fancy braces here is I can get a heads and then a 1, a heads, and then a 2, a heads, and then a 3, a heads, 4, heads, 5, heads, 6. But then I can also get a tails 1, a tails 2, I can get a tails 3, tails 4, tails 5, and then tails 6. So these are all my options. How many outcomes total? I have 12 outcomes total. Okay? So this is technically my answer, 12 outcomes in all of this. That's basically intuitive. That's not a lot of mathematical thinking, right? We basically just know that, okay, if I toss a head, I can have a head. If I toss a tail, I can have a tail. But then after I toss each outcome, I can do a 1, 2, 3, 4, 5, 6. I can do 1, 2, 3, 4, 5, 6 if I do tails. So these are the overall outcomes in my probability of experiment with tossing a coin and rolling a dice. Okay, I have 12 outcomes. That's not that hard. And that's pretty much what we're going to be going through today. So tree diagram, what we just did was a basic tree diagram. So a tree diagram gives us a visual display of the outcomes of the probability experiment. So it can be used to find the number of outcomes in a sample space as well as individual outcomes. But it doesn't need to be used, okay? You don't need to write this section down, but events are usually represented by uppercase letters, by the way. So A, B, or C. And so an event that consists of a single outcome is what we call a simple event. Okay? So in example 1, the event tossing heads and rolling a 3 is a simple event and can be represented as A, that event, equals H3. Okay, because heads and a 3. Now, whereas the event tossing heads and rolling an even number is not so simple because it has 3 possible outcomes. It can have heads and then 2, heads and 4, and heads and 6. So this idea of what an event is, whether or not it's simple, is if it's simple, it has one outcome. If it's not simple, it has more than one outcome here. And this was the tree diagram that we literally just did. Okay, we just did that tree diagram. How to identify simple events? Again, we're going to go through this. Remember, a simple event is one option. Okay, one option. So for quality control, you randomly select a machine part from a batch that has manufactured that day. Event A is selecting a specific defective part. Okay, so since this is the only thing, a specific defective machine part, this is what we call a simple event. Why is it called a simple event? Because there's one outcome. You either select the machine part or you don't. So since there's one outcome, it is what we call a specific or simple event. Okay, awesome. Now this one, you roll a 6-sided die and you want to roll at least a 4. This is what we call not a simple event, because if I say at least a 4, what that definitely includes is that your numbers could be 4 and above. So if I list out my sample space here, I can roll a 4, I can roll a 5, and I can roll a 6. That's more than one option. So since this is 3 outcomes, that means that this is not a simple event. So since there's 3 outcomes here, I can roll a not a simple event or event, whatever. I can roll a 5, 6, or 4 because I can at least have more than 4. It's not a simple event. But if I said, what's the probability of rolling a 4? That is a simple event because it is one outcome. All right, let's erase. Identifying simple events. I'm going to skip this because this is more or less just the exact same stuff that we went through, unless you really want to go through it. But it's on the key, and that's why I have the key. So go ahead and if you want to go through that, check your work, and then go to the key over here, scroll down, and then this right here, you ask the student's age, and then we can go over here, you ask the student's age. So if you want to know these answers, it is on the key. I'm just not going to explain it. I think I explained it adequately before. And I'll do that periodically throughout this lesson as well. So I'll skip these two, and we'll get right into the fundamental counting principle. The fundamental counting principle, what is that? We abbreviate that as FCP. The fundamental counting principle says this: if one event can occur in m ways and the second event can occur in n ways, then the number of ways the two events can occur is in sequence m times n. This rule can be extended for any number of events. So it doesn't have to just be 2 events. It can be 3 events, 4 events, 5 events, 6 events. It can be however many events you need. One way to think about this is basically thinking like this: a number of ways that event can occur in sequence is found by multiplying the number of ways one event can occur by the number of ways the other event can occur. Now, if that made no sense to you at all, think about it. If you want to find the number of ways something can happen, okay, you multiply the number of ways one event can occur by the number of ways the other event can occur. The best way to think about this is Chipotle. If you've ever been to Chipotle, it's amazing. They have like 2 sets of rice, 2 different kinds of beans, about 5 different meats, 3 different salsas, 2 different cold dishes, and then you have cheese, and then you have lettuce, and then you have guac, and those 3 different kinds. So they're each a different set. So you can actually multiply how many different bowls can you make with Chipotle, right? And that's the cool part about it, because it's a sequence of events. Or if your wardrobe, how many different ways can you wear something? You multiply the number of pants you have, the number of socks you have, the number of shoes you have, the number of shirts you have, and so forth. And you can actually pretty much get the number of different ways you can actually wear clothes from your own wardrobe. That is the fundamental counting principle. It's just multiplying things together. That is all it is, I promise. So let's just say you're purchasing a new car, right? The number of possible things are the manufacturers, car size, and colors. So the manufacturers, you have 3, Ford, GM, Honda. Car size, you have compact, midsize, and the color, you have white, red, black, green. Now, how many different ways can you select one manufacturer, one car size, and one color? Now, it asks to use a tree diagram. I'm actually not going to use a tree diagram. You can see it on the key there. For the sake of time, I'm just going to show you what it is, but I do show you the tree diagram on the key. I'm just not going to show you here. let's just use a fundamental counting principle. So I have 3 different cars, 3 different manufacturers, times 2 different mid-size car size, 2 different car sizes, and then times 1, 2, 3, 4. I have 4 different colors. When I multiply all this, I get 24. I get 24 different ways. So 24 different ways tells me how many ways that you can select one manufacturer, one car size, and one color, if these are the options. Okay? If these are the options, I can take 3 times 2 and then times 4, because there's 3 manufacturers, 2 car sizes, and 4 colors. Okay? Let's erase. And then let's just say it's the exact same thing, but now what it's asking is your choices now include a Toyota, a large car, a tan, or a gray car. So that means we're adding 2 different colors here. So we're adding a tan car and a gray car. And then we're adding a large car here. And then we're adding Toyota. So now how many different ways? Well, now I have 4 different manufacturers, so 4 times. I now have 3 different car sizes, and now I have 6 different colors. So what will that equal? That actually equals 72. So this is 72 different ways I can actually buy a car if these are the options. Okay? It's that easy, guys. It's just multiplying stuff together. Okay, it's just multiplying stuff together. It's that simple, I promise. All right, now what if we use a fundamental counting principle in a different way, like access codes? So the access code for a car security system includes 4 digits. So that's what it is: 1 digit, 2nd digit, 3rd digit, 4th digit. Each digit can be either 0 or 9 and all the way through, so 0 through 9. So how many access codes are possible if each digit can be used only once and not repeated? What does this mean? So think about it. If I can use 0 through 9, how many is that? You should not be thinking 9. You should be thinking 10, because 10 is including 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You'll actually get 10 of these. So 10 digits. Okay? So the first one is only once, can be only once and not repeated. So my first digit, I can use all 9 numbers, or sorry, all 10 numbers, right? But my second digit has to be 1 less than that, because I can't repeat that number. So that means my only available options now are 9. My available options now will become 8 and then 7. So now what do I have? I have 10 times 9 times 8 times 7, which gives me 5,040 different combinations. So these are the different access codes, different ways that I can make the access code. Now, what if each digit can be repeated? So let's go back here. Let's erase this. What if each digit can be repeated? That's a great question. So if each digit can be repeated, that means I have 10 times 10 times 10 times 10. So that means I literally have 10 times 10 times 10 times 10, which is the same thing as 10 to the 4th power, which is the same thing as 1 with 4 zeros behind it. So that's 10,000 different ways. I have 10,000 different access codes, if it were. Okay? The next one, each digit can be repeated, but the first digit cannot be 0 or 1. So what does that mean? That means the first digit can be repeated, but like every digit can be repeated, but the first digit cannot be 0 or 1. So what's my first option here? So for the first digit, if it can't be 0 or 1, can be any other number, yeah. So if I start out with 10 numbers, guys, if I start out with 10 numbers, but I can't use 2 numbers, that means how many numbers am I left with my first digit? I'm left with 8, because it's 10 minus these 2 numbers, which gives me 8. But every other digit can be repeated, right? So that means I could do 10, 10, 10. So I have 8 times 10 times 10 times 10, which gives me 8,000. So this is 8,000 different access codes I can use and can be using. Okay, awesome. I'm going to erase. And this next couple examples is really just continued. Remember, I'm not going to show you this because this is just kind of checkpoints. So see if you can do it on yourself. Check yourself with the key over here. Okay, find example 4 on the key. So just scroll down. Example 4 should be right here. This is example 4 continued. So this is the license plate number right there. Feel free to use that and check it. I'm not going to go through them. I'm going to go to the types of probability. Okay. There's actually 3 types of probability. The first one is what we call classical. It's theoretical probability. It's basically used when each outcome in the sample event is equally likely to occur. So all things being considered, they're equally likely to occur. This is the classical probability for an event given by this. So you'll be writing down this formula. If you're following along in your notes, you can write it down. Okay? Awesome. So what does this mean? The number of outcomes in event E over the total number of outcomes. You roll a 6-sided die, guys. A 6-sided die, and then you want to find the probability of each event. So rolling a 3 and rolling a 7. So this is where I'm going to start using probability notation. We say the probability of rolling a 3. This is how I write it. The probability of rolling a 3. Well, there's 1 3 on the 6-sided die, and then there's 6 different outcomes total. So number of outcomes in event E. So this is event, right? So this is the event I'm interested in. Rolling a 3. There's 1 3 over the total number of outcomes in the sample space, and the total number of outcomes for a 6-sided die is 6. So that means there's 1 outcome in 6 options. And this, of course, can be simplified down to 0.167. Whether or not it wants a decimal or a fraction, Math Excel may ask you for a decimal, Math Excel may ask you for a fraction, but either way, this is what it is. So this event could be said to say A equals 3. This event rolling for B, we can say this event B is the same thing as saying rolling a 7. So again, probability of 7. Can I roll a 7 out of a 6-sided die? No, it's not possible. So that means it's 0 options available out of 6 different options. And so this, of course, is 0. That's just not possible. Okay, it's not possible to roll that. This is what we call a null event. Okay, that means that's just simply not possible no matter what, given the circumstances of the 6-sided die. Given that it is a 6-sided die, it is impossible for you to roll a 7. All right, let's move on. Let's go. Okay, so C, rolling a number less than 5. This one's a little bit tricky, but let's list it out here. How many different options do I have? A number less than 5. I can say that less than 5 is 1, 2, 3, and 4. Now notice I'm not including 5 because it's less than 5. So C equals this many events, or this many outcomes, 1, 2, 3, 4, not 5 because it's not including 5. And so that means I can have the probability of X is less than 5 equals, how many numbers are these? 4. And then out of how many total? 6, which reduces down to 2 all over 3, which as a decimal is 0.667, or roughly around 66%. Okay, so that is how you would do probability. Very, very basic theoretical probability. Let's erase. Let's continue with classical probability. I'm going to go through this because these are cards. Now I will show you on not on Desmos, on your classwork page. If you go to classwork for Google Classroom, if you scroll down, you'll see on probability right here, you'll see this probability deck of cards. You can absolutely feel free to use this. If you're not familiar with a deck of cards, this is actually tells you a 52 standard deck of 52 cards, and it will tell you what's in the standard deck. Okay, because I'm going to assume that you guys know how many queens we have in a deck, how many aces do we have in a deck, how many black cards do we have in the deck, and so forth. But use this, click on that PDF. It's just found on Unit 7, Probability Deck with Cards, to help you navigate that. So if my probability is selecting a 7 of diamonds, okay, so this is what it is, the probability of selecting a 7 of diamonds. That's my diamond here, okay? What is that? There is actually only one 7 of diamonds in the whole 52 card deck. Okay? And so it's 1 out of 52, and this reduces down to 0.019, about 1%. So getting about 2%, about getting the 7 of diamonds is about 2%. What about selecting just a straight diamond? So the probability of selecting a straight diamond, okay, there's actually 13 diamonds in the deck. Again, use that PDF that I showed you. There's 13 diamonds on the deck out of 52. This reduces down to 1/4, which is, of course, 0.25 or 25%. Okay? What if I want to select a diamond, a heart, club, or spade? So if I want to find the probability of selecting a diamond, okay, or a heart, or a club, or a spade, that's kind of what my spade looks like. That means I have all 4 suits, right? So all 4 suits are a diamond, heart, club, or spade, which means I have 52 cards out of 52 cards, which means that this is 1 or 100%. Okay? That means, of course, if I draw from a standard deck of 52 cards, I will absolutely, no matter what, pick up a heart, club, spade, or a diamond. Okay? So that is how you do it with cards. Now let's get to empirical probability. Empirical probability is my second type of probability. It's also what we call statistical probability. It's actual events, like me observing the actual events of certain things. So it's really just how many times something occurs over the number of times, the total number of times it occurs. So when an experiment is repeated many times, regular patterns are therefore formed. This is true. So these patterns make it possible to find empirical probability. So what does that mean? That means empirical probability can be used even when each outcome of an event is not equally likely to occur. Okay, you don't really need to know that too much, but let's go to an example. A company is conducting an online survey of randomly selected individuals to determine how often they recycle. So far you have 2,541 people have responded to the survey. The frequency distribution is below, and we're going to be asking this. What is the probability that the next person that responds to the survey says they always recycle? Says always recycle. Okay? So we have this right here. This is what it is. And this is, if you're following along in your notes, you would be actually writing this down right here. You would be writing that down, the total. Okay? Now, let's find out the probability of always. So the probability of always. So we have 1,054 people voted that over the total number of people that actually voted. Well, I got that flipped. Over the total amount of people who voted, so 2,541. And this, of course, reduces down to 0.430. Math Excel will more than likely ask you for a decimal version like this. Okay? Not too bad, right? I just take this and then divide it by the total. I mean, that's really what it is. Okay? So let's just say I have another similar example here. So conducting a survey so far, 975 people have been surveyed. So what is the probability that the next user surveyed is about 23 to 35? So right here, 23 to 35. And then I go to my total. Okay. Make sure you write that down if you're following in your notes. And then this is age 23 minus 35, and then equals It's going to be 312 all over 975. This, of course, reduces down to 0.32. Boom. Okay? Not too difficult. Let's erase. Continue. All right, so the law of large numbers. What is the law of large numbers and how does it relate to subjective probability, which is our third type of probability? Law of large numbers is this, and the experiment is repeated over and over, and the empirical probability of an event approaches the theoretical. So this is actually what it looks like, guys. I think this is really cool. I mean, just pay attention. Like, look at this. So, of course, the probability of tossing a head or a tails of a coin is 1/2, right? That's a theoretical probability, right? But watch this. So I can toss, this is the proportion of our heads, okay? And this is the number of tosses. So as I first start tossing it, it's kind of like all sporadic, right? It kind of is all sporadic. But as I start doing it more often, more and more times, over and over and over and over and over again, the probability, the proportion starts to just be 1/2 over and over and over and over and over again. Okay, so that is what it says. The empirical probability starts to approach or diverge into what the theoretical probability is. Of course, this is 0.5. So when you do an experiment over and over and over and over again, you start to actually see that this experiment will diverge, or really converge, rather. It will converge into your theoretical probability. I think that's pretty cool. Okay, so definition, this is the third type of probability, subjective probabilities. Subjective probabilities are really just from intuition. They're educated guesses or estimates. So for instance, given a patient's health and extended injuries, the doctor may feel that patient has 90% of full recovery. Okay, so you're not really going to be doing too much with subjective probability. You're mainly just going to be doing this. You'll have to basically just say, okay, is this probability subjective, theoretical, or classical? So the probability that you will be married by age 30 is 0.5. Of course, you don't know that. So in this case, it is what we call subjective. Okay. The probability that a voter chosen at random will vote Republican is 0.45. This is actually something that we have data on, and that is what we call empirical. Since we have data on that, it's empirical. It's actual events that's happening. Okay. And of course, this last one, probability of winning a $1,000 ticket raffle, not $1,000, but 1,000 ticket raffle is one ticket is 1 out of 1,000. This, of course, is what we call theoretical. Theoretical or classical. This is what we call classical probability. Okay, so I hope that kind of makes sense. The distinctions there, I'm going to erase and we're going to continue. The range of probabilities rule is actually very simple. You should know by now the range of probability is between 0 and 1 inclusive. That means the probability has to be in between 0 and 1. It has to be greater than 0 but less than 1. Okay? The probability of 0 is a null event. It's also what we call a 0 chance of it occurring. Probability of 1 is a certain event. It's a 100% chance of occurring. So I can say that's a 100% chance that it's going to rain in Arizona today, maybe tomorrow. Then that means it's what we call a certain event given the circumstances. This right here is just a fancy symbol for sigma. It just means addition. That's all it means. So addition, adding the probabilities all the way up, and you get 1. We're going to deal a little bit more about that next week. So the sum of all the probabilities equals 1. Another thing, unusual events are highly unlikely to occur. So if an event is unusual, that means it's highly unlikely. And these events are usually occur with a probability of less than 5% or 0.05. Okay, so sometimes Math Excel will ask you, is this an unusual event? Well, if it's less than 5%, then it is. If it's 5% or greater, then it is not an unusual event. Okay, so like drawing the diamond, the 7 of diamonds, that was about 2%. So that's an unusual event if I get the 7 of diamonds. Okay. So let's move on. Complementary events. Complementary events. The complement of events E is the set of all outcomes. Let me move this here. Okay, the complement of events E is a set of all outcomes in a sample space that are not included in event E. The complement of E is denoted by E prime. That's how we read it, E prime. All right. What does this mean? It means if, let's just say it's a 75% chance of raining outside tomorrow. What's the complement of it not raining outside? Well, you would take 100% minus 75%, and then you would get 25%. That's what it means. Okay, so everything that's not included into the set. So let's look at this Venn diagram, E. So E is 5 and 6, right? Well, not E then, if you're looking at a six-sided die, would be 1, 2, 3, 4. That would be what's left. So if you roll a 2, okay, what you didn't roll was a 1, a 3, 4, 5, and 6. If you toss the heads, what you didn't toss is a tails. So that's what the complementary events say. And this is what the formula is, and this is how you derive the formula. So probability of E plus the probability of not E equals 1. Okay? So when you add those two together, probability of it raining outside, 75%. Probability of it not raining outside is 25%. 75% plus 25% equals 100% or 1. It's a certain event. That's something. It's either going to be raining or not raining outside. Okay? Probability of E equals 1 minus probability of the not E. And then, of course, you can move this around and simplify it to be this. So the probability of not E is 1 minus probability of E. So we're going to be doing a lot with that. Let's look at a couple examples. Use a frequency distribution in example 7. So I want you to just go back, flip through example 7. And to find the probability of randomly selecting a social networking site user who is not between 25 and 35 years old. So the first step is the probability of age 23. Yeah, this should be 23. Sorry. That should be 23. 23. And then minus 35. This was actually, 312. So look back at example 7. In the chart, the ages between 23 to 35 was 312 out of a total of 975. Out of a total of 975. Okay, this probability is 0.32 when I solve it and simplify it. Now my second step would then be to find the probability of it not, and that's what the squiggly line means, that if it not, squiggly line, or tilde, age 23 to 35. So that means I just take 1 minus 0.32. And 1 minus 0.32 is just 0.68. So this is the probability, this is a complement of not selecting a user that's 23 to 35 years old. Okay, that's a complement. So first step, find what the actual probability is, which is this. Second step, subtract that from 1, and then there you go. Next one, use the frequency distribution, example 7 again. What about 18 to 22-year-olds? So 18 to 22, so the first thing I need to find is what is the probability of actually selecting 18 to 22-year-olds? And if you look at your chart, this is actually 156 all over 975. And so this is approximately 0.16. I'm going to use that probability in my second step to find the probability of not. Now you can write it like this way too. I know in the first example I used a squiggly line. In this one I'm actually going to use my complement, so I'm going to use the prime here. They mean the exact same thing, the prime or the squiggly line. It just means not. It means a complement. So it literally means the same thing, so don't freak out about that. This equals 1 minus that probability that I found in the first step, and this equals 0.84. Okay, very simple stuff, very simple, very applicable. I hope that makes sense. Let's erase. Now, this probability 11, I'm going to skip 10 because 10 is a little bit, you don't really need to know 10, but go on the key that I posted on Google Classroom, go on the key and then kind of peruse 10. It's not complicated, but it kind of talks about tree diagrams a lot. So these are like applications, and example 10 kind of goes through applications and stuff. So if you're interested, go on the key, but I'm not going to go through it. Example 11 says this: your college identification number consists of 8 digits, so we're going to be using the fundamental counting principle and using the application for it. Each digit can be 0 through 9, and each digit can be repeated. Okay, so that means the first step, I'm going to write this. If it's 0 through 9 and it consists of 8 digits, that means I'm going to literally write 8 things. So 1, 2, 3, 4, 5, 6, 7, 8. And then, since it can be 0 through 9, that means I have 10 digits each. And because it's a fundamental counting principle, I'm going to multiply those all together. This actually equals 10 to the 8th power, which is a rather lengthy number, 1 with 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. So it's 100 billion. Or 100 million, sorry. It's 100 million. So that means it's 100 million different combinations that you can have. So this is 100 million ways that you can actually make your combination, your identification number. Now the second step asks you, what is the probability of getting your college identification number when randomly generating 8 digits? Okay, so this is a little bit more complicated. But when randomly generating the 8 digits, just the 8 digits here, what is the actual probability of getting it? It's actually very simple. So I'm just going to say the probability of randomly generating those 10 digits, I'm just going to write this, randomly generating the 8 digits. Wow, I can't even spell. Look at that. Randomly generating the 8 digits. Wow, what am I doing here? Okay, it's just going to be, surprise, 1 all over 100 million. So 1, 2, 3, 4, 5, 6, 7, 8. Now, of course, you can get a decimal for this. I'm not going to find a decimal. It's a rather small decimal. It's a very slim probability, obviously. So what this says is, okay, this is how many different ways your identification number can be listed, and this is the probability of actually selecting that combination the first time. Okay, it's a rather small probability. It's a pretty cool application, to be honest with you. I think it's a pretty cool application. What did we learn today? We learned to identify sample spaces. We learned the fundamental counting principle. We distinguished between classical, empirical, and subjective, and we determined the probability of a complement of an event. And then we used the tree diagram and the fundamental counting principle to find probabilities. We did all of that. What is your homework? Your homework is 3.1 Basics of Probability. You now know the basics of it. Please do that on Math Excel and be prepared for the homework quiz tomorrow. Tomorrow we're going to go through the bell work, and that's going to go over some questions that you may or may not see on the homework quiz. But until then, this is C Squared Mathematics. Please like and subscribe. Peace out, Phantoms.